Let's now conduct a shell balance on this single fin. The differential volume over which we'll conduct the shell balance is given by a length dx. There's a conductive heat current coming into this differential volume given by Q sub x, and a heat current which leaves this differential volume given by Q sub x plus dx. Convection carries heat away from all faces of this fin. Even though a moment ago we discussed how most of the heat loss occurs from the face defined by L by W, there is a way of handling the heat loss by convection from all four faces of this differential volume, which can be done relatively simply. So we'll do that here. The perimeter of this differential volume is 2W plus 2T. The cross-sectional area is given by W times T. Our assumptions are that we are at steady state, that we have a constant cross-sectional area, there's a constant thermal conductivity, and there is no generation of heat. We can construct a shell balance. The shell balance has Qx double prime, the heat flux coming into the fin, through a cross-sectional area A sub C. The product of those is the heat current that enters. We then have the heat current that is leaving, which is given by a product of the heat flux, Q double prime x plus dx times A sub C. And we also have heat leaving due to convection, which is given by a heat transfer coefficient times the perimeter times dx. P times dx defines the surface area of that differential volume, and that times T minus T infinity, the driving force for heat removal. Notice here that T is a variable. It depends on what position we are at along the fin. That defines the driving force for convective heat loss. We can rearrange this expression and take the limit as dx goes to 0, obtaining this expression. And we can plug in now for Qx double prime using Fourier's law. And now everything is in terms of the temperature. We can also define the boundary conditions. Boundary condition is T at x equals 0 equals T sub B. This is the temperature at the base. And then we also need a boundary condition at the tip of the fin. Boundary condition at the tip of the fin involves conduction in the fin being equal to convective loss at the tip of the fin. This is from the face defined by T and W. Hence, we have minus K times A sub C times the derivative dt dx evaluated at x equals L. That's the conduction that comes into that face defined by T and W. And on the right-hand side, we have H times A sub C times T evaluated at x equals L minus T infinity. This is the convective heat loss at that face defined by T and W. We'll define some new variables, which will make it easier to solve this governing equation. We're going to define an excess temperature theta, which is T of x minus T infinity. This is just how much temperature we have at a given point along the fin relative to the bulk air temperature. So that's our driving force for heat transfer. We can also define the excess temperature at the base, theta sub B, which is T sub B minus T sub infinity. We also define a constant m. This constant is defined as m equals the square root of h, the heat transfer coefficient, times the perimeter, divided by the cross-sectional area times the thermal conductivity. The usefulness of this constant is really only apparent in the context of the governing equation. So let's plug it in. If we plug in these definitions, we find this governing equation with the second derivative of the excess temperature with respect to x minus m squared times the excess temperature equals 0. We also have our two boundary conditions, one based on the temperature of the base of the fin, that it's theta sub b, and a second boundary condition at the tip of the fin, where conduction has been set equal to convection. If we look at this governing equation, what it's saying is that the second derivative of a function must be equal to a constant squared times the function itself. That's what will satisfy this governing equation. The solution to this differential equation must involve hyperbolic functions. These are sinh and coshs. Note that sines and cosines do not satisfy this function. That would be off by a negative sign. Sinh and coshs are collections of exponential functions. I suggest looking either at Wikipedia to learn more about these, or at our written lecture notes, which go into more detail on the properties of sinh and cosh functions. Although the solution to the problem that we've just defined is possible, it's a bit involved. So we're going to swap out one of the boundary conditions for one which is a bit simpler. At this end face of the fin, we said before that we have a Newton's law of cooling type boundary condition. We can replace this with an insulated tip approximation. This means that we are enforcing a no flux condition at the end face of the fin that is defined by T and W. And mathematically, that is d theta dx at x equals L equals 0. The general solution for our governing equation is theta of x equals c sub 1 times the exponential of m times x plus c sub 2 times the exponential of minus mx. Here we've written the solution out in exponentials since those are probably more familiar with you, but you can see that once you apply the boundary conditions, you can gather up terms and make this look even simpler using hyperbolic cosines. So the final solution, which involves having applied our boundary conditions, is theta over theta sub b, which is a dimensionless temperature, equals cosh of m times L minus x divided by cosh of m times L. Because the argument of the cosh needs to be dimensionless, this means that m times L does not carry units. This means that m times L is a dimensionless distance. M is non-dimensionalizing L. We can now plot this solution, which will give us some physical insights into this temperature distribution. For a given value of m, we can obtain a profile that looks like this. At x equals 0, the temperature is T sub b, and at x equals L, it's at a smaller value of the temperature. We see that the slope of the temperature profile is 0 at x equals L based on our boundary condition. We can then plot this out for a larger value of m. Physically, a larger value of m means that we have a larger heat transfer coefficient h or a smaller thermal conductivity k. If the heat transfer coefficient h is larger, that means we're better able to remove heat from the fin. If the thermal conductivity is smaller, this means that heat has more difficulty in conducting down the fin. Both of these will result in there being a larger temperature gradient going down the fin. This means that there's a bigger temperature difference, so for larger values of m, we expect curves that are lower in this schematic. Another way to get physical insight into our solution is to plot the temperature at the tip of the fin as a function of m times L. So we can take the temperature of the fin and evaluate it at the tip. And so we have theta divided by theta sub b at x equals L. This is the dimensionless temperature. That it equals 1 over cosh of m times L. And 1 over a cosh is simply a hyperbolic secant. So we have a hyperbolic secant of m times L. You can plot the solution using your favorite plotting package, and the solution looks like this. On the y-axis, we have theta over theta sub b evaluated at x equals L. And on the x-axis, we have m times L. What this is physically saying is that for larger values of m, the tip of the fin approaches T infinity. In other words, if we have more effective conductive heat transfer, Or if the thermal conductivity is lower, the tip of the fin is more likely to be at T infinity. It's important to consider if it's actually a good thing if the tip of the fin is closer to T infinity. If it is at T infinity, that's an indication that this heat sink might be much larger than it needs to be. And of course, from a product perspective, it may not be desirable to have a product which is now much heavier than necessary due to having this oversized heat sink.